Okay, Algebra 2, we're going to get going into section 2.7 right now. And this is one of the first times this year, but absolutely not the last time, that we're going to learn how to graph really a new style of function, one that I think you guys probably haven't seen before. And it's going to look maybe a little bit daunting at first, but hopefully we're going to get the hang of it pretty quickly and talk about two ways to do these graphs, one of which kind of explains it better, the other of which, though, is a lot faster way to do it. So let's dive in. What we're doing here in 2.7 is we're talking about absolute value functions and then the graphs of those functions going along with them as well. But before we get too far into this, probably a good idea to have a little discussion right here about what the term absolute value actually means. So it's one that I think you guys have been dealing with for a few years, but just in case we need a refresher here, absolute value means the distance between a number and zero on a number line. So the symbol for absolute value is two vertical lines with a number in between. So you would read this expression right here as the absolute value of 5. Although most of the time when I'm drawing it by hand, those absolute value symbols can kind of look like an 11 if you're not careful. So I'll usually put them at a little bit of an angle, kind of something like that. So when we talk about absolute value, it's a question of distance. How far is that number from zero on a number line? So if you remember number lines back when you did them in pre-algebra, we normally would put 0 in the middle. Now, of course, there's no center to a line, but that's usually how we draw it. And 5 is going to be 5 units over here to the right. So when we're talking about the absolute value of 5, we just want to know what's the distance between this number, 5, and this number, 0, on the number line. And that one's pretty easy to see. That distance is 1, 2, 3, 4, 5 units away. And that is why the absolute value of 5 is just equal to 5. Hopefully you guys remember a little bit about that as we move forward. Okay, couple of quick statements right here. Actually, I guess let's go ahead and talk about something else before we get there. Now, going along with that, if I now were to ask you about the absolute value of negative 5, let's go back to this definition. The absolute value of negative 5 means the distance between that number, negative 5, and 0 on your number line. So now I would plot negative 5, which of course is going to be 5 units over here to the left. So let me do this in green here. So there is negative 5, that number right there. And if I wanted to know its absolute value, I'm asking you what's the distance between negative 5 and 0 on your number line. And that distance right there is also 5 units. And that is why the absolute value of negative 5 is also 5. So when we're talking about distance, we're talking about a quantity that can't be negative because there's really no such thing as a negative distance. So, two quick statements right here, true or false. Statement A, absolute value is always positive. And then statement B, absolute value is never negative. Now, a lot of people look at those two statements and think that they are exactly the same thing. They are not. The answer to this, I'll let you guys think about it for a second. To the first statement, absolute value is always positive, that is a false statement. And the reason for that, there is one tiny little counterexample that refutes it, everybody. The absolute value of 0. If I'm asking you now to think about a number line and to think, okay, here's 0. How far is 0 from 0 on your number line? The answer to that is 0. And unfortunately, 0 is not a positive number. So because of that one counterexample, that's why statement A is false. But statement B, absolute value is never negative, that statement is true. You are never going to get a negative number here for your answer to an absolute value statement. Almost all the time it will be positive, but not quite all the time because you can get 0 from that result. Okay, let's move on to another page right here, and let's talk about just evaluating some absolute value expressions. Once you get the hang of this, guys, you should whip through this like there's nothing to it. Actually, it's the exact number I was just using right there. Must have been in the back of my head. The absolute value of 5 in example A, 5 is how far away from 0? 5 units. So basically, the long and short of it, guys, when you're taking the absolute value of a positive number, absolute value has no impact, and you just end up with the exact same positive number again. But when absolute value is useful would be an example like B. When you're taking the absolute value of a negative number, you just need to think, okay, on my number line, here is 0. Somewhere over here to the left is negative 11. And what's the distance between negative 11 and 0? The answer to that is 11. So we just said in example A, absolute value has no impact at all on a positive number. But in example B, if you're taking the absolute value of a negative number, you take the opposite of that negative number and it turns positive. Okay, me and my big mouth, we already talked about C. The absolute value of 0 is 0. That would be the one case there where absolute value is not positive. And I wanted you to look at D and E together here, everybody, because by themselves, they're not super interesting. Let's take a look at D. It's the absolute value of 12 minus 10. One thing I want to make sure you guys know is that absolute value is actually a grouping symbol. It kind of works like parentheses or brackets in that you do what comes inside the absolute value first. So what we're going to do here, everybody, is take the 12 minus 10 first and simplify that. So that becomes the absolute value of 2, which equals, just 2. Now E is almost the exact same question, except now you'll notice I've reversed the order of subtraction. So again, we do inside the absolute value first. The 10 minus 12 is going to become a negative 2. So we're now taking the absolute value of negative 2, and that's going to give us an answer of positive 2. So what I wanted you to see from this here, guys, is that example D and example E both have the exact same answer, even though we have reversed the order of subtraction. Just kind of an interesting little tidbit right there that happens with problems like that. Okay, and you know what? I think we're actually going to skip what's going on slide number 3. This is not hugely important here moving forward, so I think we can live without that. But let's move on to this here. Graphing absolute value functions is the really important thing that we're going to talk about here today. And the way we're going to graph our very first example, f of x is equal to the absolute value of x, is a method that we're going to come back to almost every time this year we learn how to graph something new. It's not the most efficient method in the world, but it always works. And that method, you learned this probably back in 6th or 7th grade, is the method of making a table here and choosing x values and figuring out what y values are going to complete the statement then. Now, what you kind of want to avoid is getting a little bit too boring with your x values. Let me show you what I mean. What I'm about to do here is not wrong, but if I put in 3 and then 2 and then 1 for my x values, and in fact, you know what? Let me go ahead and put 0 in there as well. You're going to get kind of an idea of what's going on, but not entirely. Let's see what happens with y here. Remember, everybody, that the f of x and the y are really kind of the same thing. So over here on the side, I'm going to write this concept right here. Y is equal to f of x, and of course that could be g of x or h of x or anything like that. So what's going on here? We're going to put a value in for x and figure out what y is equal to. So when x is 3, y then is the absolute value of 3, which equals 3. And we just came up with the ordered pair 3, 3, and that's our first solution to this equation. If you put a 3 in for x, y is equal to 3 as well. Now, 1 point is not good enough to tell us what this graph looks like, so now let's let x equal 2. And the absolute value of 2 is 2. So now we have the ordered pair 2, 2. There's a second solution. When you let x equal 1, you take the absolute value of 1 and get 1. So 1, 1 is our third solution. And when you put in 0, the absolute value of 0 is 0. So the origin is a solution as well. And you've got to be careful about making a table of values, because sometimes if you don't look far enough, you can get yourself thinking you know what's going on when in actuality you really only have about half the picture. It certainly looks, don't write this in your notes, guys, it looks like this is just a linear function, a straight line like what we've been dealing with earlier here in Chapter 2. But I need to remind you here, absolute value doesn't get interesting until you start putting in what kinds of values for x negative numbers. So I'm going to go ahead and complete this table now by putting -1, -2, and -3 in for x, and let's see what we get for y. When x is -1, we're going to take the absolute value of -1, which equals +1. So now we have the ordered pair -1, 1, and when I plot that, whoa! All of a sudden now, guys, for the first time this year, we now have an equation that is not linear when we graph it, because you can't draw one straight line that passes through all 5 of these points. Let's keep going, guys. When you put in -2 for x, the absolute value of -2 is +2. So now I'm going to plot -2, +2, and that's this point right here. And when we plug in -3, the absolute value of -3 is +3. So I've got the ordered pair -3, +3. And what we have now, guys, are 7 solutions to this equation. And that 7 is probably good enough to tell us something that we didn't know before. The shape of an absolute value graph is a V. Okay, it's got a ray there on the right and a ray over here on the left up into the second quadrant. And that is what the graph of y equals the absolute value of x looks like. And it is important, everybody, that we jot this down. What we are dealing with right here, guys, let me put a star by this. This is something called our parent graph. And I may have used that phrase back in our notes on section 2.6. A parent graph is one graph that you guys are going to have memorized, and all of the other graphs we're going to do in this family of functions are going to be variations off of that one theme. So a parent graph is one that you guys need to know. I want to point out 3 quick things about this particular parent graph. First of all, this point right over here, guys, has a name. That is called the vertex of your absolute value graph, and in this particular example, that's at the ordered pair of 0, 0. You'll see why that's important here a little bit later. The second thing, everybody, is to realize that this V we've made up here is actually comprised of 2 different rays. And if you remember a ray from geometry, it's a set of collinear points with one endpoint, and it goes on forever in just one direction, as opposed to a line segment, which has 2 endpoints, or a line which has no endpoints and goes on forever. So our graph here in blue is made up of 2 rays, each of which has a slope. This ray over here on the right has a slope equal to, let's count it, guys, from the origin we're going up 1, right 1, up 1, right 1. So that's a slope of 1 over 1, which just equals 1. So we need to know that about our parent graph. The slope of the right-hand ray is +1. And on the left-hand ray, if I went from this point to this point, I'm going down 1, right 1, down 1, right 1, down 1, right 1. That right there is a slope of -1. And that is the slope of your left-hand ray on the parent graph. So these 3 things, everybody, the vertex at 0, 0, and the slopes of 1 and -1 are pretty important to know about this particular parent graph. Actually, one other thing I'll point out that looks really, really obvious now, this graph right here opens upward. It's a V that's pointing up to the top like that. So that's a 4th thing to notice about this parent graph. And I bring all that up because we are now going to graph, let's see, I think I've got 5 more examples for you guys. We are not going to take this much time with any of the next 5 examples. What we're going to do is use this concept of a parent graph right here, and then we're going to take all of those transformations that we learned how to do in section 2.6, and we're going to use those to our advantage to come up with these graphs in a far more efficient manner. And you guys should like efficient because it means fast. All right, let's take a look at example B. F of x is equal to the absolute value of x minus 4. So what I want you guys to notice is, I'll undo this in just a second, if that -4 wasn't there, this would be the exact same graph as the one that we just got done with right there. That's our parent graph. But what's happening here, guys, is there's a -4 at the end of this function. And if you remember back from 2.6, a number that's either added or subtracted at the end of a function is a vertical shift. It's either moving you up if k is positive or down if k is negative. So subtracting 4 here is going to take our parent graph and move us down 4 units. So you don't need to do what I'm about to do right here, guys, but in green with a dotted line, that is the parent graph that we just got done graphing right there, okay? So again, you don't need to write that out, but that in green is the parent graph of y is equal to the absolute value of x. What we're going to do now is take advantage of this k value right here and simply shift this entire graph down 4 units. So on the parent graph, our vertex was right here at the point 0, 0. Now we move that origin point down 4 units, 1, 2, 3, 4, and our y-intercept is right there. You don't have to label this, but you'll see why I am in a second, at the point 0, negative 4. That, you guys, is the only shift that happens here. It's not moving horizontally, it's not reflecting, and so I draw everything else exactly the same. The next couple points are going to go here and here and here, and you'll notice I'm graphing a ray right here with a slope of positive 1. And then on the left-hand side, we go up 1, left 1, up 1, left 1, up 1, left 1, and that now means that we are drawing a ray over here with a slope of negative 1. That graph in red, guys, is our answer. That's the graph of f of x is equal to the absolute value of x minus 4. Let's test that real quick. If you choose any point that's located on that graph, it should work when you put it in here. So even though I said we weren't going to do this, I'm going to just to test my answer, I'm going to make a quick table of values. If x is 0, let's put that in here and see what we get out for y. Okay, the absolute value of 0 is 0, and then when we subtract 4 from that, we get negative 4. And the ordered pair 0, negative 4 is on this graph. That's a really good sign that we're doing things right. Now I'm going to just randomly choose one other point. I'm going to choose this point right over here that was on our graph. And if I've done this right, that looks like the ordered pair negative 3, negative 1. So I think negative 3 for x should get us negative 1 for y, but let's try putting the negative 3 in here now. The absolute value of negative 3 is positive 3, and positive 3 minus 4 is negative 1, and that's the solution right there that we had. So I chose 2 points that were on my graph. They both worked out. I feel pretty good about having gotten this answer right. So all of the work that I did here with the table and the testing of the points is a good idea, but it's really not necessary. All we really needed to know is that this graph was our normal parent graph, but shifted down 4 units. All right, let's take a look at another variation on this. At first glance, example C looks almost identical to example B, but when you look more closely, you realize there's a minus 4 here, but now that minus 4 is taking place inside the parentheses. So this would be the second thing we talked about in 2.6. This is what we call a horizontal shift. And with a minus 4 inside the parentheses, that means that we are shifting this graph to the right 4 units from the parent graph. So again, in green, I'm going to draw my parent graph. You guys don't need to do this, but it's not a bad idea. So this right here would be the parent graph of y equals the absolute value of x. And now we're going to shift this graph 4 units to the right. I'll start with the vertex and move that 4 units over here. And that's the only change. So I graph one ray with a slope of positive 1. So up 1, right 1, up 1, right 1, up 1, right 1. There's the right-hand ray. And then the other ray, up 1, left 1, up 1, left 1, up 1, left 1. That one has a slope of negative 1. And that is what this ray looks like. And guys, I'm done. If I wanted to make sure I got it right, let me choose a couple of random points. I don't know, this one right here. That looks like the ordered pair 6, 2. Let's make sure it works. let's put a 6 in here for x, and the first thing we're going to do is subtract 4. 6 minus 4 is 2, and the absolute value of 2 is 2. So we got that one right. Let me pick this point over here, though, guys. That is the ordered pair 0, 4. Let's see if that one works. So let me just erase those lines right there, and let's try it. Putting a 0 in for x, 0 minus 4 is negative 4, and the absolute value of negative 4 is positive 4. So we put in a 0 and we got 4 out. This ordered pair is correct also. And guys, as a general rule of thumb, if you tried 1 point on the right ray and 1 point on the left ray and they both work, there's like a 99.9% chance that you got the whole thing right. Okay, so that's what's going on here. So as a reminder, I'm not sitting here making a table of values for every single one of these problems. I could do that if I wanted to, but it's much, much faster if we learned those transformations that we talked about in section 2.6, and we can use those. We did some vertical shifting in example B. We did some horizontal shifting in example C. Now let's take a look at what's going on here in D. This is one of the trickier ones right here, guys. F of x is equal to 3 times the absolute value of x. There's no vertical shifting here because there's no k being added or subtracted at the end. There's no horizontal shifting here because there's no h being added or subtracted inside the absolute value. But what there is, everybody, is a constant value of 3 being multiplied by your absolute value of x. So what that does, this was what came at the very end of our notes in section 2.6. What we have right here is called a vertical stretch. We are, there's an extra T there, I always forget. We are stretching this graph out to be 3 times as tall as it normally would be. And remember, guys, when you make something taller, let's see if I can do this right here. If you took your stick figure here, and there you go. If you make something taller, what you're actually doing is you're making it appear skinnier, even though it's really the same height that it was. So let's talk about what that looks like for our purposes here. Once again, let me go green with this one. I'll try to be consistent with you guys. Once again, I'm going to draw my parent graph here in green with a dotted line. Vertex at the origin, and then you have one ray here with a slope of 1, and a ray over here with a slope of -1. Here's what a vertical stretch looks like. First of all, any point that was already on the x-axis stays on the x-axis. So the vertex of this graph is still now going to be at the ordered pair 0, 0. Now I said I wasn't going to do this all the time, but let's just check this real quick. 0 for x. The absolute value of 0 is 0 times 3 is 0. So yeah, that point is right. But watch what happens, guys, when I put in a 1 for x. The absolute value of 1 is 1 times 3 is 3. That gets me the ordered pair, well, not 1, 1 like I had on the parent graph, but now I have the ordered pair 1, 3. It's located right there. Watch what happens when we put in 2. The absolute value of 2 is 2 times 3 is 6. So my next solution, the ordered pair 2, 6. And I'm going to kind of run out of room here, guys, but that, all right, is what the ray on the right half looks like. If I were to put in -1, all right, let me erase some of this junk right here, and let's try this again. The absolute value of -1 is 1 times 3 is 3. So I get the ordered pair -1, 3. Oh, and if I put in -2, absolute value of -2 is 2 times 3 is 6. -2, positive 6. Okay, so now I'm still seeing the V shape that we had before, but if you look back over here at my stick figure, I'm hoping you guys can see what happened. That green graph has been stretched vertically. It is now 3 times as tall as it was before. Now, how does that actually show up in the graph? One thing that I want to point out right here, guys, the slope of the original green ray was 1. But if you look at the blue ray right above it then, guys, the slope of that ray was up 3, right 1. That's a slope of 3. And then over here on the left, you'd go up 3, left 1. That's a slope of negative 3. So what happens here, guys, is that this value right here, which we called A, that gives you the slopes of the two rays here. So your slopes of the rays are plus and minus A. Positive 3 over here on the right, negative 3 over here on the left. That's what the plus or minus there means. So that's a really good thing to keep in mind as we start looking at some other variations on this. But again, there's no H, there's no K, and that's why the vertex here was still located at the ordered pair 0, 0. That one didn't shift at all. All right, 2 more here, guys, then we're about done. E is just a variation on what we did there in D a second ago. This time, though, everybody, you have the absolute value of x, and I'm sorry, my smartboard doesn't do a good job of this. If I was writing it by hand, it would look like this. F of x is equal to, that's a negative 1/4 times the absolute value of x. Okay, first thing we need to do now, locate your vertex. Actually, hang on, before I do that, all right, my parent graph, again, just like always, the parent graph looks like this, vertex at the origin, and slope of 1 and negative 1. Okay, so for our parent graph now, everybody, H and K, there's no number being added at the end, and there's no number being added or subtracted in the middle, so the vertex remains at the ordered pair 0, 0. But 2 interesting things happen right now. First of all, we have a coefficient out in front of this absolute value of 1/4. If we go back to the last example, the coefficient of 3 meant that our slopes here were positive and negative 3. Now in this example, our slopes, this case, are going to be plus and minus a coefficient right here of 1/4. The other really interesting thing, though, that we have not dealt with in any of the previous examples at all, you guys, is the fact that this coefficient out here is negative. And if you remember what a negative leading coefficient does, that, everybody, is a vertical reflection over the x-axis. That's when you take something and you flip it this way over the axis. What that does for us, guys, is unlike every graph that we've looked at so far, which has opened upward, now that we're flipping this thing, this graph is now going to open downward. So that's 2 interesting changes right here. We've got slopes of plus and minus 1/4, and our graph opens downward. So, don't draw this yet, but for the first time we're going to be drawing a V that looks something like that, although I got to be more careful about how I did that. The one that goes down and to the right is actually going to have a slope of negative 1/4. I'm going to go down 1 and right 4 units. And again, down 1 and right 4, and that, everybody, is what one of the sides of this V looks like. And for the other one on the left, I'm going to go down 1 and left 4 units. Down 1 and left 4 units, and that is what the second part of this graph looks like. And again, if I wanted to make sure that I got this right, let me choose a couple of random points. Like this one right here is the ordered pair of 4, negative 1. Let's make sure it works. The absolute value of 4 is 4. 1/4 of 4 is 1, and the opposite of that is negative 1. So that one works out. How about this point right over here? Looks like negative 8, negative 2. Let's see if that one works when we plug it back in on the top. So here we go. The absolute value of negative 8 is 8. 1/4 of 8 is 2, and the opposite of that is negative 2. That point works as well. So again, if you got one on the left and one on the right and they both work, then there's a really good chance we've got that right. So I suppose if I wanted at this point, I could erase my parent graph. There you go, guys. That's what that graph in blue looks like. That is the graph of f of x equals negative 1/4 times the absolute value of x. And one last example, guys. Let's put it all together now. This one has a lot going on here. 4 minus 2 times the absolute value of x plus 3. Okay, what I decided to do here, guys, was throw, let me see, 1, 2, 3, 4 different things at you all at once. The first thing I did here that's just kind of mean is I gave you this in a different order that's probably not the way you guys would like to see it. You've got a constant in front here of 4 and then a -2 and then the x. So the way you guys would probably prefer to see this written would be the -2 in front times the absolute value of x plus 3, and then that 4 can be added on at the very end. Now, the significance of that is that this version is more in line with what you guys are used to seeing. First things first, there's a number added at the very end right there. That means that our graph is moving up 4 units. The next thing I see, there's a +3 inside the absolute value. That means that this graph is shifting left 3 units. Now, when you put those two pieces of information together, that tells us that our vertex, instead of being at the point 0, 0, is at a point that's left 3 units from the origin and up 4. That is the ordered pair -3, 4. And that should be our vertex. 1, 2, 3 to the left and 4 units up. Now, you really want to make sure right now that you're doing this correctly, because if you goofed up your vertex, everything else is going to be wrong. So it's not a bad idea to stop and check right now. When I put in -3 for x, I should end up with 4 for y. Let's try that. -3 for x plus 3 is going to give us 0. That's a good sign. The absolute value of 0 is 0. 0 times -2 is 0, and 0 plus 4 is 4. So check, we got our vertex right. So the +4 at the end, the +3 in the absolute value, those are things that tell us where to locate the vertex. Two other things now. The negative in front of all this is going to tell us that our absolute value graph is going to open what direction? Anytime it's negative, it's going to open downward, not upward. And that a value of 2 means that the slopes of your rays are going to be positive and -2 coming from that origin. So I've already plotted the vertex. That's our blue dot that's located right over here. We know that it opens downward, so it's not going to do this, everybody. That would be opening up. What we're doing instead is something that's going to open downward like that, but I've got to be careful and I've got to get my slopes right. For a slope of -2, I'm going to go down 2, right 1. Down 2, right 1, down 2, right 1. And that's probably enough to give me the right-hand ray. Sorry about that. There you go. And now for the left-hand ray, this is a little bit counterintuitive. That left-hand ray is actually the slope of +2. But rather than going up 2, right 1, this has to open downward. So we're going to go down 2, left 1. And that's the same thing as +2. Down 2, left 1, down 2, left 1. And this is what the left-hand ray looks like. Now, one more time, we checked the vertex already. Let's check another point. Like this one over here is 0, -2. Let me put that in right here, and let's make sure that works. When x is 0, 0 plus 3 is 3. The absolute value of 3 is 3. Times -2 is -6, and -6 plus 4 is -2. So check. That one worked out. Let's try this point right over here, which looks like it is -4, and it looks like it has a y value of +2. So now, all right, let me get rid of some of this. All right, when we put in -4 for x, we should end up with +2 for y. Let's check it. -4 plus 3 is -1. The absolute value of -1 is +1. +1 times -2 is -2. -2 plus 4, yep, is +2. That point works out as well. So at this point, I feel really confident about my answer. All right, guys, that's as much as I had for you here in section 2.7. It's a tricky little section, but hopefully we've seen enough variations on our parent graph here that you guys are going to understand how that works. So let's give the 2.7 homework a try. Let me know how that goes. Good luck, everybody.